What are we going to do today? So we are going to continue our study of MaxFlow. So I believe Nathan left you with the Edmonds-Karp algorithm and the sort of explanation. We were left at the spot where we're trying to explain how that algorithm works. So what I'm going to do today is, since it's been a week, briefly go over the MaxFlow problem, the formalization. The algorithmic framework that we talk about is the Ford-Fulkerson method. So just like with minimum spanning trees, remember we came up with this big idea, this cut theorem for the minimum spanning trees, and then all of the algorithms that we came up with were essentially specific implementations, specific applications of that cut lemma. Well, similarly, with MaxFlow problems, there's going to be this very strong principle. It's the notion of duality, and it's this MaxFlow is equal to the min-cut theorem. And that is going to drive all of the algorithms, at least all of the algorithms that we're going to study. So we first studied this first algorithm, the Ford-Fulkerson algorithm. We discovered that there were some possible efficiency problems with that algorithm, so we studied this heuristic called the Edmonds-Karp algorithm. It still uses the same idea as Ford-Fulkerson, but we can have a tighter analysis. Now, in the graduate version of this class, we take this even further. So our favorite data structures person, the guy who came up with the Fibonacci heaps and did all that stuff with the minimum spanning tree stuff, Tarjan, he also has this notion of push-relabel style algorithms. It's a different algorithmic framework for solving MaxFlow, and you can use push-relabel to get beyond the runtime complexities that we have. We don't talk about it here, but if you're interested, and this is all of the implementations of these things are actually straightforward. So if you're interested, I'm happy to make more materials available to you. So what we'll do today, Edmonds-Karp, so review of MaxFlow, Edmonds-Karp, why it works, and then some neat applications of MaxFlow min-cut. So things like solving bipartite matchings, which is very critical to sort of scheduling problems. We'll talk about flight scheduling. So for example, if you're a company and you want to fly your executives to some retreat, perhaps you don't want to put them all on the same flight. That would be perhaps risky if you're a Fortune 500 company and you put all your execs on one flight. What if the flight's late? I mean, the whole vacation would be ruined, right? Or even worse, if it was a flight that had some mechanical trouble, then your leadership might be imperiled. So you of course want to find different ways to get all your executives to Hawaii, because it's very important for them to be there. So that type of constraints, we'll talk about edge disjoint paths, node disjoint paths, and then a very cool application of MaxFlow min-cut to baseball elimination. So the question, will my team possibly make it to the playoffs? Turns out, for baseball, you can solve this problem using an application of MaxFlow. So one of the first, it's not a paper, but it's a paper, but it wasn't published. One of the first things that in grad school, my fellow office mates and I, we asked a similar question for basketball. So if you think about those basketball pyramids, brackets. So for the March Madness, you basically fill out a bracket and then you do this competitively with your friends, and money is involved. The person who has the closest guesstimate to the actual outcome, there's some scoring system. So everybody know what I'm talking about? Because I'm certainly not doing a good job explaining this. So those brackets, those are fun with sports, right? It turns out with baseball, you can solve this in polynomial time using MaxFlow min-cut. With basketball, the fun with sports. So answering the question, tournament has started. We are in the middle of the tournament, and I have a schedule and you have a schedule. Is it possible for me to win or not? Answering that question turns out to be NP complete. So, kind of very cool. This is why I think it's fun. So, let's go ahead and get started. MaxFlow. Everybody remember the motivation that we had for this problem. It was this rail network in Europe. There was, practically you would like to figure out the minimum number of rail connections you have to remove in order to separate the Soviet bloc from Western Europe in the case of an invasion. And that was one of the motivations behind this particular problem. So the way that mathematicians formalize this combinatorial problem, so we have a graph with vertices and edges, and we have two distinct nodes, a source and a sink. And each of the edges have capacities. So we have some capacity function which maps the edges to, we can make this real numbers, but let's just make them rational numbers, right? So rational, all right? And the problem is we'd like to send flow along this network. So the edges are kind of like, the edges of the graph are like pipes, and we'd like to send like an abstract notion of flow. And this flow could represent all sorts of things. In the case of this troop movement situation, it actually represents trains, but we can think of them as many things, and time and money and so forth. So what we'd like to do is find some function f, which maps the edges to numbers as well. And of course, if that was the only thing, if we just had to put numbers on edges, then we could assign everything to 0, and that would, it wouldn't be very interesting. So we have to add constraints to the type of flow that we want. And the constraints are essentially, they're very natural. So the first constraint is that the flow on every edge has to be less than the capacity of that edge. That was the point of the capacity, represents the maximum amount of flow you can put on that edge. So that's the capacity constraint. And the next is the flow constraint, which means essentially input and there's no excess flow at any node. All right, so for every node that's not the source of the sink, we would like the inflow of node V to be the outflow of node V. Okay? And another way of writing that is to say that the flow that is going in to V should equal the flow that is going out of V. Okay? And then finally, we have the actual measure of this flow. Do you remember what that was? Remember, the goal of this problem is we are trying to push flow from the source to the sink. And by flow, it means we want to assign a number to each edge. That number should be less than the capacity of that edge. At every node, we shouldn't have more stuff coming in than going out, or vice versa. And overall, we're going to measure the value of this flow as what? Yeah, so essentially, or for the source, and we're going to find that this is going to be the same as the sink because of this flow constraint. But essentially, we're going to measure the flow by saying, let's take all the stuff that's coming out of the source and subtract all the stuff that's coming into the source, and that's going to be the value of our flow. Okay? So given a graph, we would like to compute this value. Over every possible flow that's valid, we would like to find the flow that has the largest value. Okay? Okay. So I think we went over examples. This was an example of a particular flow. The red value is always going to be the flow, and this is always going to be the capacity. What do I want to say here? Many applications, I'll certainly show you several. That brings us to, so that's the definition. That's the problem definition. Now your natural instinct, after having just studied greedy algorithms, is that we could probably find a greedy algorithm for this flow problem as well. And we're almost correct. The algorithm is almost greedy. There's just one little twist in it. And let's try to understand why we need that twist. So I'm sure that Nathan went over this particular example. All right? If we are to say, let's solve this MaxFlow problem by finding the path that has the most flow that we can push and going ahead and pushing that flow through the network. Right, so the greedy algorithm that we might consider is find the biggest flow, push, and continue until you can no longer push. And this example right here should illustrate why that approach doesn't exactly work. All right, so for example, in this graph, what is the path that allows you to push the most flow? Here, I'll make it easy for you to tell me the answer. What's the... Yeah? Yes, SABT. Right? And as we talked in last class, you can push 20 units along this flow, but then that basically saturates this edge and this edge. Right? And so you're essentially going to be left with the graph that looks like this. This has capacity 10, 10, and 10. The right approach was not to push 20 across. Right? The right approach was to send 10 along this path and 10 along this path. Right? The right path is to do essentially, right? Everybody see why the yellow path, there's a way to push 30 along this? Right? Okay. So the problem is the greedy approach led us to make an incorrect decision at some particular point. And the way that we're going to get around this is to, so the greedy decisions could possibly let us into a local minimum, some situation where we've pushed 20 and we can push no more and we're stuck. So the thing that's going to get us out of this bind is to augment our graph, allow us to undo some mistake that we might have already made. And that mechanism for undoing a mistake that we've made consists of what? What's that concept? Anybody remember? We had a special name for this. It's not exactly backtracking in the... It implements some form of backtracking, but not in the same way that you think about when you're doing tic-tac-toe or something. We had a concept. Did you go over the notion of residual graph? Okay, good. So that is what I'm looking for. Okay? The idea of a residual graph is going to allow us to undo any mistakes we might have made when we take greedy decisions. So the high-level solution to this family of MaxFlow algorithms, it's going to be, yeah, sure, take any choice you want, but leave a way for you to undo that choice later on. And that's the form of this residual graph, right? And so this is, intuitively, I'm not going to define it formally here, but it's essentially whenever you push X units from U to V, so whenever you push flow across some edge, the idea is to create a residual edge in a new graph from V to U with that same exact capacity. And so the idea is you're going to be able to, you're going to allow yourself to undo, even partially undo some of the flow that you've pushed in the process of looking for another path from S to T. Okay? So the best way to go through this, yes. And of course that leads to the notion of an augmenting path. This is, right, so for any flow that you currently have, any legal flow that you're currently working with, you can use that rule and come up with a residual graph GF. Okay? And essentially an augmenting path is any path from S to T in some residual graph that you have. All right? And so this is an example of a residual graph. If you're pushing, remember this red value is what is the flow, and this right here is capacity, and these blue edges are the residual edges. So since I'm pushing 1 unit of flow, Since I'm pushing one unit of flow from S to A, then I'm going to create a residual edge from A to S with capacity 1. Okay, so in this entire graph, every time I'm pushing some flow from one node to the other, I'm going to create a residual edge in the opposite direction. Take, for example, this situation in which the original graph from H to I already has two nodes from H to I and I to H. So if we're going to push one unit of flow from H to I, yeah, okay. So there's an error in this graph because, so let's go through the analysis here. This is a good example. So the original graph has two edges from H to I, and the original capacities are 3 here and 2 here. Since we are pushing one unit of flow from H to I, that means we need to create a residual edge from I to H with capacity 1. Since we already have an edge from I to H with capacity 3, we're going to combine these and change the capacity of this to 4. Okay? Similarly, since there are 2 units of flow from I to H, we're going to need to augment the capacity of this to also be 4. Okay? So when edges already exist in the graph, you can combine the residual edge with the original edge and just increase the capacity. Remember that the only thing that these residual edges currently have are capacity. All right? So everybody have one of these handouts? Yeah? Okay. I would like to go over, so raise your hand. Does everybody feel comfortable with the way that the MaxFlow algorithm works? I wanted to go over an example, and I don't know if Nathan did that in class. Did he? So here is this graph right here with all of the, this would be the input right here. This is a graph that consists of the edges and weights, and these black numbers are the capacities. And so we would like to apply our methodology for solving MaxFlow on this graph. And the idea, which we haven't given a name yet, is to continue to find paths from S to T and push flow along them, add residual edges, and continue until there are no more paths from S to T. Okay? So fortunately, this example only involves 6 steps. So I'm going to do the first step, and then I'd like you to pair up and do the remaining steps to make sure you understand. So I know the numbers are quite small here, but since you folks are much younger than I am, you will have no problem reading these small numbers. Let's go ahead and go through this first example. All right, so the algorithm says find any path from S to T. And just to keep it fun, we'll find one of these zigzag paths which basically go like this. So this is our first augmenting path. We would like to push flow along this path. How much flow can we push? Why can we only push one unit? There is a bottleneck edge right here, this one right here, which only allows us to push one along this path. So of course, once you find a path, you find the bottleneck edge on that path. That's how much flow you can push during this iteration. So we're going to push one unit of flow along each of these edges. Since we're pushing one unit of flow, we're going to say, okay, right here, this edge right here, it will change to, we're pushing 1, and the capacity is 3. We're pushing 1, and the capacity is 2. We're pushing 1, and the capacity is 1. And now we're going to add our residual edges. We'll add the residual edges in blue. So since we're pushing one unit of flow from S to A, we need to create a residual edge from A to S that has capacity 1. And similarly, we're going to need to create a residual edge with capacity 1 and a residual edge. So did everybody follow the residual edges that I had to add? Now there's also one edge that we're going to have to remove from this graph because it no longer has any capacity. Which edge would that be? From H to B. Right? Okay. So in the next step of our algorithm, I see. Okay. So in this set of examples, I've slightly modified the semantics. This second number is not the capacity, like I've showed right here, but it's the remaining capacity. Okay? And this edge right here, since we're pushing 1 unit of flow in this direction, we're pushing 1 unit of flow and there's 0 remaining capacity, and so the edge is gray. Okay? So what I'd like you to do, there are only 2 more steps in this algorithm, and then we're done. So to make sure you understand, the next path that I would like you to consider is this path right here. That is an augmenting path from S to T. By the way, this right here is GF1. So it's the residual graph after we pushed our 1 unit of flow from SAHB IT. All right? So with your neighbor, please try to figure out how the graph changes after you push this, after you push along this particular path. Right?
How do we know which path to take?
So you can take that's the spoiler alert. The algorithm is correct no matter what path you take.
So how do we know, like, okay, we're going to take this arbitrary path, now we're going to take this arbitrary path, then we're going to take some other path? How do we know that?
We're going to use, so you can use any method for finding a path between S and T. And eventually, as we'll see at the end of this, there will be no longer any paths from S to T. When that happens, you're done. We'll understand why we're done based on the MaxFlow min-cut theorem. Okay, so we're going to push 1 unit of flow from S to B to H to T. And so that means since we're pushing 1 unit along each of these edges, we're going to increase the flow and decrease the capacity for each of these edges. So here we're going to change each of these to this. And now we're going to add the residual edges. So since we're going to add a residual edge from B to S with capacity 1, so we'll just merge the current existing edge with that residual edge and change the capacity of this to 3. Here we'll add this edge back and put this capacity back to 1. And here we'll add another edge with capacity 1. So we should end up with this resulting graph. And now there's only one more step, and that's this path right here. Question? So in this slide or the previous? Okay. In the previous, why did I well, because look at what I'm pushing. I'm pushing from S to B to H to I to T. So since I'm pushing flow across B to H, that means that there has to be, I have to add a residual. Oh, yes, you're right. That's what you meant. I need to add a residual edge like this. And that I'm going to combine with this edge that disappeared. Did that answer it? Yeah, you were right. The edge should be from H to B. Question? In this graph, is there a path from S to A to where? Yeah? Yes. I arbitrarily picked this top one, but there is a path from S to A to H to B to I to T again using this particular edge right here. Yeah, so the point, we'll eventually get to this, the point is that the Ford-Fulkerson algorithm works no matter which paths you take. No matter which path you get from S to T, eventually you're going to finish. We'll see an example very shortly where if you pick paths haphazardly, it could take longer. Okay? And then eventually with Edmonds Karp, we're going to say, look, pick the shortest paths first, and in fact you can end much quicker. Question? How do you know what? When to end. So we'll see in the very next slide. Okay, so I'm going to skip the actual computation of the numbers, but this is what the graph, this is how the graph results after you take that top green path. And now let's imagine we follow our algorithm, which is let's find an augmenting path in this graph. Notice that there are no longer any paths from S to T. In fact, the only way you can go is from S to A. Once you get to A, you're stuck. You can go back to S, but that's not a flow. So at this point in this graph, there are no more augmenting paths. And that means that you're done. Question? Why is the one from S to B grayed out? Because when we did this flow right here, when we pushed, there was a capacity here. When we pushed across that edge right here, this edge no longer had any capacity. Its capacity was 0. So we gray it out because we can no longer use it. It's as if it's not in the graph. This is a residual. Yes, this should also be, this should be grayed out too. Yes, you're right. Good. Yeah, this should be gray. Now, a natural question you should ask yourself is, greedy algorithms typically, they're very subtle and hard to figure out. So why should I believe that what Abhi just said, which is, hey guys, just do a greedy thing, but keep track of this extra augmenting path business, and then when you're done, when you can't find any more paths, you're done. Why would this be correct? And what I want to show you is that a result of this algorithm, when there are no more augmenting paths from S to T, here's something you can do. Let's consider all of the nodes that you can reach from S. So in this case, the only nodes that we can reach from S are S and A. Okay? And in particular, if we look at this original graph, so what am I trying to say? When you get to this point, when you can no longer find a path from S to T, consider all of the nodes that you can reach from S. Okay? Clearly you can't reach all the way to T, because otherwise you wouldn't be done. But you can reach some subset of nodes. And if we look at those same subsets in the original graph, like right here, look at all the outgoing edges from this subset. The only outgoing edges are this one and this one. And so in particular, what this says is that if we partition this graph into two parts, S and T, the max that you can actually push across S and A is going to be 3. And so if we're thinking back to the railroad problem, if we got rid of that edge from A to H and from S to B, there would simply be no way to push any flow from S to T. In other words, SA, this cut of this graph, where we take this part and the other part, so SA and BHIT, it's a partition of this graph. And in particular, the max flow that you can push across this partition is 3. In other words, this cut and there could be, notice that there are other cuts that are much larger. So for example, if we were to take this cut, what's the value of that cut? Does everybody see this? You could actually push 11 from this situation, right? Question?
So it's the maximum capacity ignoring the
Yeah, yeah. It's only how much flow you can push out of S, because that, yeah. All right, so why do we know that this is correct? Because in previous class, you proved this lemma, right? Which is that for any flow and for any cut, the maximum value of that flow is upper bounded by the value of that cut. And so in particular, when you find a flow and a corresponding cut that have the same value, you know that you cannot increase the flow because it would violate this. So this is why this algorithm works. Because, and any Ford-Fulkerson-like algorithm works, because once there are no more augmenting paths from S to T, that means you can circle all of the nodes that you can reach from S. And you know you can't reach T because there are no augmenting paths. So the argument is essentially circle all the nodes, and now you know that the edges across this cut, they're saturated. The flow is pushing, you're pushing that unit of flow because, in fact, if you weren't pushing 2 units on this edge, then that means you could push flow to H, and so H would be pink as well. So the reason that Ford-Fulkerson works is because, in the end, you construct both the flow and a cut such that the value of this flow is equal to the value of this cut. Okay? And by MaxFlow, and so by the lemma, there cannot be a larger flow because every flow has to be smaller than this particular cut. Does that make sense? I believe Nathan went over the proof of this. He told me he did. So, does this give everybody a sense? This is a very powerful idea that it's called duality. And the idea is that if you can show that the maximum value of a problem that you want is upper bounded by the minimum of some other problem, then you could kind of solve them at the same time, and you'll know when you've got your best answer, because your best answer is when these things are equal. All right? It's the same idea if we get time later on. Any zero-sum game, like poker, for example, has a strategy, a min-max strategy, where you can, essentially the value of this game, the value of poker for somebody, is going to be the maximum value that you can minimize. We'll get to it later. It's a zero-sum game, and so there's a min-max theorem there as well. Okay, so once you have this lemma, which is that for any cut f and st, the value of f is upper bounded by the value of this cut. By the way, you remember that the definition of a cut here is just going to be, it's going to be the capacities of all of the edges from S to T. Okay, and so once you have this lemma, then it follows that you can make an argument that this max flow is equal to the minimum cut. Okay? What I really want to get to, so that suggests that you start with the flow that's at 0, and while there's some augmenting path in your residual graph, you augment your flow with the bottleneck edge, just like we were doing in our example. Now the problem, right, the high level is that the problem that we had, which we saw in last class, was that if we just pick paths, if for example we if we select this path right here, then we're going to basically have pushed one unit of flow across this edge, and now we can select this path right here and push flow again from S to T. Now, since all of the capacities in this example are integral, this means that every time we find an augmenting path, our flow is going to increase by what? At least one. At least one, right? In this example, certainly. But in any graph example, where let's say the numbers are integral, okay? Your flow is going to increase by 1, and then, so that means that the maximum number of loops that you're going to have to do is basically f star, where this is the max flow. So in this example, we know that Ford-Fulkerson is going to guarantee that there are at most 50 iterations of this. That's not a very compelling answer. In fact, okay, the root of the problem is we're picking bad paths. And now we're going to begin a very beautiful argument for why if we do just something slightly better, we get a much, much better algorithm. Our algorithm no longer depends on the answer, the value of the answer. You could imagine a flow that if you multiply the problem values by 1,000,000, if you multiply each of the numbers by 1,000,000, you shouldn't have to be doing 1,000,000 times more work. And that's what Ford-Fulkerson guarantees. Edmonds-Karp is going to say, no, we're going to actually do this much sharper. And so the idea is that we're going to pick the paths from S to T that are the shortest by number of hops. So let delta F, let this value right here just as be the number of hops So delta F SV, and we can in fact just ignore the S there. Delta FV is just going to be the number of hops from S to V along the shortest path from S to V in our residual graph.
When we say shortest path, do you mean shortest by number of hops, or we aren't using capacity?
We're not using capacities. It's shortest by number of edges. Right? And if you think about this, that would have been your first guess too. Why are we taking these extra one-leg hops? Why don't we just find the shortest path, which would be this one and that one? So your instincts here would be pick paths well. By the way, how can you pick the paths that have the smallest number of edges? Breadth first search. Dijkstra's, exactly. Except a special case of Dijkstra when all of the edge weights are 1, which turns out to be breadth first search. Yeah? Very good. Very good, very good. Okay? So, here are the two facts that we have to show in order to make this mechanism work. Okay? The first is that as you proceed by adding more and more augmenting paths, the shortest path from S to V never goes down. So, what does it mean? It says delta I plus 1 of V is greater than or equal to delta I. So if you think about it, okay, so this could be the shortest path. Let's say that's the shortest path from S to V. That's at time I. That's after you've done I iterations of this augmenting paths. When you consider the next augmenting path, either that augmenting path never touches any of these edges, in which case the shortest path remains the shortest path, or one of these edges is affected, in which case the edge is removed and a new residual edge is added. And certainly removing that edge, removing this edge can never make a path shorter. Okay? If there was a shorter path without that edge, then that would have been the shortest path. Okay? So this is not a very important point, but it's a natural one. And essentially that shortest paths from S to any node in the graph, they will never go down as we continue in this algorithm. That is going to bring us to the main point of this Edmonds-Karp algorithm, okay? Which is that whenever you push, this is the key point of the analysis. Whenever you make an augmenting path, some edge is critical. What does it mean by critical? And this is why I say that Olivia Newton-John has some influence in our graph, because some edge has to get critical along any augmenting path. And when that edge becomes critical, like for example this one, it actually gets removed from the graph. So the point of the analysis is that the edge that's critical along an augmenting path. Everybody know what a critical edge is? That's the one where the amount of flow that you're pushing is equal to the capacity of that edge. And that critical edge is removed in the next residual graph. And so here's the question that we're going to ask. How many times can an edge get critical? Yes. So, very good point. So, what you're saying is that if we pick paths willy-nilly, then an edge can go critical, essentially F, like where F is the value of the max flow. But we are going to be picking paths based on their shortest path. And that's going to be the difference. In fact, you've highlighted the key point. An edge can go critical many times if we just pick paths willy-nilly. But if we're always picking the shortest path from S to T, then an edge can go critical at most V over 2 times. Okay? And the reason for this is as follows. First of all, what's the longest path that you could have from S to T? V minus 1, yeah, V, let's say. And so the longest path can be V. And what I'm about to show you, the crux of this argument, is that every time an edge goes critical, it goes 2 steps farther from S. And intuitively, so this argument is a little bit, it's a little bit subtle, but I'll give you the very short summary of this. So we consider some edge from U to V. And if we're going to push flow across this right here, what happens to, and let's say this is the critical edge. So once we've pushed flow, and that's the critical edge, what happens in the very next time step? That edge gets reversed. Okay? And now, how can the edge from UV, the edge from UV no longer exists. How can it become critical again? What is the first step that has to happen before UV can go critical again? Someone has to push flow. The empire has to strike back. And there has to be a path like this. Right? And this edge has to become critical there. Now already you see this was at some time, right? At some time this was a path we picked. So it was the shortest path. Okay? Then this edge got reversed. And now later on, this became the path. And so this had to be a shortest path. Okay? And I'm going to have to write this argument out or go over it at the beginning of class because I won't be able to finish it in a few minutes. But I do want to highlight the main idea, which is that an edge becomes critical. It becomes flipped. To go critical again, you have to have a path, a strike back path. And then finally, the second time that the edge goes critical, I'm going to argue that the distance from S to U had to increase by 2. So the first time it was critical, this was the distance. The second time it was critical, it has to increase by 2. That's the point that I want to make. So every time an edge goes critical, its distance from S grows by 2, which means that it can only go critical V over 2 times. Because the first time it's going to increase by 2, the second time it's going to increase by 2, the third time it's going to increase by 2. The V over second time, it's going to have increased by V, which means it can no longer be a shortest path. Okay? So, armed with these facts, we can come up with the faster algorithm. So, we've just argued that an edge goes critical at most this many times. How many edges are there? How many edges? Come on, easy question. E. So that means, how many times can Olivia Newton-John come into our head for the rest of the day? How can those pictures of those men come into your head? So if there are only this many critical events, and there are only that many edges, so each edge can only go critical this many times, and there are only this many edges, that means the total number of augmenting paths that we're ever going to have to find is EV over 2. Everybody agree with that? And now how much time does it take to find an augmenting path? Remember, we are using breadth first search in order to find our augmenting paths. And so the time is E plus V, which means the total running time of this algorithm is going to be E squared V. Right? So Thankfully, we've come up with an algorithm that doesn't depend on the running time, on the values of the flows in the graph. Question? That's right, yeah. You can do either. You can assume that we're assuming that the number of edges is equal to the number of vertices, connected graphs. Okay? So, we started with Ford-Fulkerson. We've come to E squared V, and Tarjan, our favorite algorithmics professor at Princeton, he has a way of doing this in EV squared, and if you do this faster, you can do this in V cubed time. So these two methods, they're not very complicated. They're actually quite simple. They are relying on this principle of like you're pouring water from the source and you're letting water run downhill and you're making sure that there's no more extra, that there's no spillage, essentially. It's a very physical analogy. Question? Yes. So there are lots. This is a very rich area. If you have multiple sources and multiple sinks, you can actually model that problem by just making a super sink and a super source. Connect the super source to all of the sources and the super sink to the thing and run that version. So you've added 2 nodes to your graph and you've got a new solution. So there are lots of situations like this. And in fact, that's what I want to actually get to, the applications. And I only have 3 minutes, but I will tell you, for example, one extremely important application of MaxFlow is bipartite matching. So here are 4 college students and 3 colleges, and as a country, we have to optimize the number of educated people. So we have to match students to colleges according to who gets admitted. Now, it could be a situation in which, let's see, we do like this. Here's a matching. 2 people get to go to college. Is this a good situation for America? Well, nobody goes to Yale, which is actually a good situation for America, I believe. So this is arguable, but another matching that we could find is something like this. Now 3 people get to go to college. And in fact, the fish goes to UVA, which might be telling. Okay, so next week we'll talk about... I still have 2 minutes. Let me do one more example. This is the edge disjoint path. So here we go. This is an airport. This is like JFK, and this is Fiji. And you want to route all of your executives from Manhattan to their vacation. These are all the intermediate flights you can take, but you want to make sure that no 2 executives end up on the same flight. Okay, because in case the flight goes down, then you've lost 2 executives. How can you solve this particular path? Edge disjoint paths. You can also come up with a version where no 2 executives can be at the same airport. Vertex disjoint paths. All right, we'll talk about these examples next class. Lunch.